All right, so we're going to finish this multiple choice section. We've only got one problem left. I'm going to go ahead and clear out all my other annotations so we got a nice clean screen, and we're looking right here at number 20. Okay, this is one of those that you could do it the same way we did the last two. So if you didn't have any trouble with those last two, once you saw how to work them, then you can do number 20 that way. Alternatively, a lot of people look and say a sub 2, that's pretty close to a sub 1. Because remember, in my formula, which was a sub n equals a sub 1 times r to the n minus 1, what we were looking for is this a sub 1. That's what we have to find. That's our missing piece. Well, a lot of people look at this one and they don't want to work it out the long way. They say, really, I need a sub 1, and I got a sub 2. A sub 2 was negative 10. Then they told me my ratio, which means every time I take a step forward, I have to multiply by 5. Well, that would be negative 50. But then I stop and think, okay, well, if I'm multiplying by 5 to go forward, to go backwards, I need to divide by 5. Well, if I divide negative 10 by 5, I get a negative 2. With that information in hand, I know it goes right here into the formula. A sub n equals negative 2 times our ratio, which was 5, raised to the n minus 1 power. And there we go. It's got to be D. Okay? Moving on to the free response section. I told you you're going to have one just like this, and so here it is. Maybe. There we go. Much better. Convert the following explicit formula for an arithmetic sequence into function notation. So our final goal with function notation is that we needed to have f of x equals mx plus b. It's basically slope-intercept form, except for we have an f of x. Okay? So to do that, first thing we got to do is we have to distribute this 4. This is connected by multiplication. We're used to seeing this 4 written here in front. It's the same thing when it's written back there. Okay? We just take it and we distribute. What I have is a sub n equals negative 6. When I distribute, I get a positive 4n and a minus 4. Well, I've got like terms here and here, so I'm going to combine them. A sub n equals 4n, and these combine to be a minus 10, negative 10. All right? Last thing I have to do is I just got to make it into function notation, which means this is where I do that little bit of voodoo where I don't really do any math. I just kind of rename things. Okay? A sub n becomes f of x. And whenever we change it, this says a depending on n. When we change it to f depending on x, we have to change the variable inside our equation. So that would be my final answer. Please do your best to try to indicate your final answer to me in some way, shape, or form. Oh, now we're on to the graphing. This part still hurts, guys. This part's still tough. Graph the following sequences for 1 through 10. That means I've got to do 10 terms. And state the function family. Be sure to label the bottom and left side of the graph with your numbers or scales, okay? You have to indicate to me what you're counting by. Well, I know with my x values, I'm counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I know that much, okay? With my y values, I'm not really sure what I'm counting by until I figure out what some of those terms are, okay? When I look at this, I know my first term, my a sub 1, it's going to be right here. It's always listed there. It's 10. What this is my common difference, meaning every step I go, because this is an arithmetic sequence, every step I go, I'm adding 15. So my a sub 2 should be 25. My a sub 3 that's all the way down through a sub 5. I'm adding 15 every step. Then I should have 85, an even 100 for my a sub 7, a 115, a 130, and a 145. So a6, fill those in. And those are all of my pieces. Now I just got to go graph them, but I've got to scale my y-axis, okay? I need something that goes as low as 10 and as high as 145. Okay? A lot of people say here, oh, I'll count by tens. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Didn't get us up high enough. I don't try to get too cute with these. After I don't want to go by tens, I think about 20s. Okay? I don't think about, now 15s would be great. That'd actually be perfect here. But most people don't think to count by 15s. And you saw me when I was doing these, I had to stop and think for a little bit to make sure I was adding right. Counting up by 15s is not natural to most of us, but 20s is. So 20, 40, 60, 80. We're good with these evens. 100, 120, 140, 160. You can finish it out, 180, 200. And guys, I'm not going to use all my graph now because 145 is only going to be up to here. But if I use from here all the way down to here, basically, that's the bulk of my graph. That's a pretty good amount, okay? I'm going to switch colors to red, and I'm going to start graphing these. My first term was 10. Well, that should be right there at the halfway point. My second term was 25, 40, 55, right under that 60 marker, 70, should be halfway between, 85, and notice I keep going back and over. A sub 7 should be a nice even 100. It is. 115. 130, and then 145. Okay? So I've got it graphed. It looks like a nice straight line like it's supposed to. Okay? Excellent. Now we're given a different sequence. And notice this one's got this n-1 up here. That immediately starts telling me it's geometric. All right? So if I want to do this one by hand, one by one, like I did the last problem, that is an acceptable way to do it, okay? You would see that your first term is 6, and then you'd multiply by -3, because that's our ratio every time. So our a sub 1 would be 6, our a sub 2 would equal -18, and we go so on and so forth. A sub 3, a sub 4, ... Now, though, I also want to show you the quick shortcut way I showed you earlier, which is you can do these in the calculator and let your table function tell you the answer. You have to go into your graph, okay? And we want to type out that information, which is 6 times, open up your parentheses, -3, close them up, raise it to the n-1, but we don't have n-1. We have x-1, okay? When we don't have that n value, we just use the letter x for it, and we press enter. Now, we don't actually graph it. You can graph this if you want. You can try it. You can zoom 6, but that doesn't tell us very much. And even if it did, it would tell us what it was as a line. And we don't want lines. We need a discrete graph here, okay? I should say we don't want lines. We want a discrete function here. We don't want a continuous function, okay? So, I don't know what to do from here. But what I was trying to do was graph these points one at a time. So if I go second table, it spits out, starting with our first term of 6, second term, -18, like we thought it would be, and then it tells me all these other ones, okay? These are getting to be some really big numbers. And look, right here we end up with this just giant, massive number. It's going to be somewhere around the 102,000 sort of range. I'll try to make sure it's not something totally, hard to deal with. So that's -1.2, and then move the decimal 5 places. So we've got to have something that's as low that's as small as +16, or really our highest positive number, which was about 40,000. And it's got to go all the way down to about 120,000. Okay, -120,000. That's a big low number. So we've got to count by large amounts. Okay, so if I think maybe 20, 40, 60, 80, 100, not quite. You might want to extend the graph a little bit. Maybe count by 40,000s. Okay, so if I do that, I've got -40,000, -80,000, -120,000, -160,000. That means I've got 40, 80, 120, and 160,000. Well, this graph's going to look a little bit awkward. I think I'm going to try to make sure the test one doesn't look quite as awkward. Okay? Because a lot of these are really close to that seam. It's going to be hard to tell.